क्या लिखा होगा? हाँ, अरे पीपीटी बहुत अरे तुम जाओ यहाँ पर देखो, सिस्टम में देखो। नहीं लगाया, इधर बोल रहा है।
Yeah, that's the one.
This one.
Yeah. Then there are three of them.
3 others.
Yeah. Sure. Yeah. So today we are going to look at three different technologies like high pressure processing, pulse electric field processing, and food radiation. these three technologies are non-thermal technologies. So, I think we will kind of discuss what are the principles behind them and the equipment and their applications. So, what is the reason these technologies kind of come into picture? Traditionally we have been doing thermal processing more than 100 years or plus. Historically we have been cooking food. So, why there is an interest in non-thermal processing technologies? While heat processing can make the food safe, the quality can be degraded with the heat processing, especially during canning. Volumetric technologies such as OMI heating, microwave heating, they can able to minimize that degradation. Still, you have to heat that material to higher temperatures, and then the cooling of those, once you reach 121, there's going to be a lot of slow process, conduction, convection process. As a result, the food processors are interested in looking at technologies that can preserve food in a different way, and the non-thermal technologies kind of provide answer. In addition, the last 2 decades, there's more interest from consumers, safe foods, healthy, nutritious food, no preservatives, and things of that nature. You can approach this in multiple different ways. One is try to develop processing oriented technologies. The second is ingredient technologies. Like I think again there's a lot of ingredients being used which are synthetic in nature, but now they are replacing them with the more natural ingredients, natural antimicrobial compounds, which has a similar functionality. And at the end of the thing, once everything is done, you're probably going to have a combination of processing technologies and ingredient technologies where you can able to accomplish some of the goals of the process. Now, the note, there's a lot talk about clean label products, but at least from the US point of view, there is no legal definition for clean label. This is a term kind of used in the common people as well as trade magazines, things of that nature, but there are no legal definition for that. So, what is non-thermal technologies? Non-thermal technologies use a lethal agent other than heat to inactivate microorganisms without destroying the nutrients. This may be used at very high pressures, electric field, UV, ultrasound, cold plasma, and generally non-thermal technologies at room temperature do pasteurization effect. Remember yesterday or like during the past lectures, we talked about pasteurization means inactivation of vegetative form of bacteria, but spores survive, so it requires refrigeration storage. So, most of the non-thermal processed food currently in commercial practice, you have to keep them in refrigeration. Now, one of the other interesting limitation for non-thermal technologies is they are variable efficacy with enzymes. So, in other words, not all the enzymes inactivated while you are inactivating vegetative bacteria. So, you have to consider that as well. Oftentimes, a simple blanching technique with the heat may be a good enough to take care of enzymes before you use the non-thermal technology like high pressure to pasteurize them to kill the bacteria. The high pressure processing basically involves application of pressure with or without external heat, so that you can make a good products. The high pressure processing commercially practiced today is essentially done at room temperature or chilled conditions, whereas you can also do pressure assisted thermal sterilization, which is essentially equivalent for canning type applications that require pressure and temperature. Now, if you look at the high pressure processing, today we talk about emerging new technology, but historically if you look at it, in 1899, there's a scientist by name Haidt in Virginia Tech Ag Experiment Station first looked at high pressure processing in a lab environment with the milk storage and other applications. So, this is kind of why the high pressure processing kind of took a longer time to get commercialized. So, I mentioned the initial applications, initial exploratory study was done in 1899, 1900. Then around 1914 with the World War I and II, I think the whole interest in the technology kind of disappeared. In 1980, Japanese looked at the world literature, then they reintroduced the high pressure processing concept into the market, and subsequently around 1985, 1990, there is a professor by name Dan Focus at Oregon. He kind of looked at it and then he started working on it, and that is how this is reintroduced in the US, and the first pressure treated product came into the market 1997. I am kind of giving you the history, kind of show you the nonlinear trajectory of new technology development. You know, like you probably work on it, and then if you do not see immediate market commercial application, do not worry, eventually if your idea is sound, this will be picked up by people and commercialized in the later stages. At the moment, FDA issued letter of no objection for two pressure assisted thermal sterilization technologies. One is potato product, another is a seafood product, but there is no commercial products available in the market, but there is a lot of interest to introduce pressure based sterilization technology. So, if you look at pressure, it is like temperature. So, pressure and temperature are part of the same thermodynamic variable. So, that means a lot of things you can do with the heat, you can also do with pressure. So, in other words, I think you can probably do more pasteurization, you can do the commercial sterilization, and you can see that the pasteurization primarily spore formers are not inactivated, whereas in the sterilization you can inactivate the spore former as well as enzymes. You can also have what they call extended shelf life food. The treatment is milder than milder than the commercial sterilization, but much stronger than the pasteurization. So, these type of processes you can do this so that you can extend the shelf life of pasteurized product, and then you also inactivate some for some of the weaker thermally resistant or pressure resistant spores. Beyond that, you can also see here pressure has number of other applications. You can be able to crystallize lipids, you can be able to use the hyperbaric storage. So, in other words, imagine you have built a pressure chamber and then apply 50 megapascal or 100 megapascal and store food for months and months, similar to a refrigeration. So, you do not need refrigeration, but you can just have a pressure chamber to store the food. And you can also extract lot of different compounds with the high pressure processing, and freezing and thawing can be accomplished. So, you can see lot of parallels to thermal processing you can be able to accomplish. More other thing is the ultra shear technology or high pressure homogenization, which involve combination of pressure, temperature and shear, so that you can have beverages and other liquid products. In terms of high pressure pasteurized products, you can see kind of couple of broad categories: meat, seafood, fruits and vegetables, dairy based products, fed foods, like a lot of them are meat products. And what I want you to pay attention is the pressure level applied and then the target bacteria. So, if you look at the pressure level applied 500 to 600 megapascal, a chill condition for meat product, and then if you look at the control, you are targeting Listeria. Whereas, if you look at seafood, you are targeting Vibrio, and the pressure levels are 200, 300 megapascal. So, it is kind of modest pressures. If you look at E. coli, listeria in fruits and vegetables, you can probably apply again 400 to 600 megapascal pressure to inactivate them. So, the take home message is you cannot just have one target organism for entire set of products. Each product category you may have a different target organism, and then you need to make sure that you address them properly. And one other interesting thing is the pressure treatment result in extended shelf life. Compared to thermally pasteurized product, you may have 1.5 to 2 times more shelf life, and but you still need to store them in the refrigerator conditions because spores are not inactivated, and because if you have a temperature abuse, there may be spore growth that can result in outbreak. So, a lot of times when they pressure pasteurized products, especially products with the low acid conditions, they tend to acidify so that they kind of suppress the growth of the spores. At the same time, you can able to have a safe product. Now, high pressure processing kind of has its origin in material science, material engineering type of thing, where they were using for water jet cutting, material densification, and supercritical fluid extraction, diamond making, those type of things. And you can see, for example, you can make artificial diamond at extreme pressures and temperatures, and this is a kind of commercial practice. When the food industry is kind of adapted, they were kind of trying to understand the technology from food product point of view. So, that is kind of the research kind of took a while to develop, and then we can be able to get this. If you never heard about high pressure processing before, when I say 600 megapascal, how high is the pressure? If you imagine you go to the Mariana Trench at probably one of the deepest portion of the ocean, it is about 100 megapascal, whereas the pressures we are using is almost 5 to 6 times more, and the center of earth is kind of much more pressure. Nevertheless, this is a extreme pressures we are kind of using for the treatment. The next couple of slides, I am going to just go through some example commercial products, why it is commercially successful. So, the sliced deli meats, as we mentioned, it inactivate Listeria, E. coli, Salmonella, and other products, and it provides a distribution. So, why Listeria, and then why deli meat, and why high pressure processing? Around 2000, there were major outbreaks in meat products. The USDA Food Safety Inspection Service, FSIS, basically said they want to have zero tolerance for Listeria in processed meat, and so they kind of provided a multiple option how meat processor can implement that. One of the options they gave was the high pressure processing, and many companies find that very practical and commercially viable. So, they introduced, since then that become much more commercially successful. So, that is around 2000. Moving forward 2025, today still high pressure processing is practiced in meat, not only for food safety reason. What they also found is, for example, in some processed meat they use nitrate, and that sometimes people worry about cancer causing issues and so on. What they found is when you do high pressure processing, they can eliminate the need for nitrate, so they have a safe product. So, that way it becomes much cleaner ingredient label, make the food safe. So, I think the it is kind of liked by both the consumers as well as the food processors. And of course, you can be able to, since the introduction of high pressure processing in meat products, there were no known outbreaks in those type of processed products. Another interesting application is oysters. So, I was working in an institution in Chicago at the time. This is around 2000 time frame. So, there is a company came and talked to us about looking at technology for oysters, because oysters normally found in sea, Vibrio bacteria is a common problem, and but consumers like to eat oysters without much cooking. So, they kind of trying to find some technological solution. We were experimenting with high pressure processing at the time. What we found is, instead of going to, when we treated around 200 to 300 megapascal, take the oysters out, they even survive the pressure alive for a couple of minutes, then eventually dead. But I think that kind of proved the concept that pressure treatment can able to protect the integrity of the muscle, at the same time kill the bacteria. So, since then the seafood industry had adapted oysters, and then they also adapted lobsters. And again, this is around 2005, 2003 time frame. One interesting thing is, initial adaptation was on food safety reason, but today even it is successful. Part of the reason is couple of benefits from this technology. One, when you pressure treat oysters, the shell and the muscle can separate, because the shell is very rigid, the muscle is soft. So, when you are pressure treating, it detaches by itself. So, the oyster industry, they call this as a shucking, and so this can be done. So, that means it is a big labor savings, and this is not previously known. So, they can able to do it, and you can see here in the lobster. So, you have a lobster with the shell, and then after high pressure treatment, the whole muscle comes out quite easily. The second thing is, when you pressure treat oysters, you can add, for example, lemon juice or some flavor agents, and then it can be infused, because pressure can do mass transfer. So, you can infuse things during pressure treatment. So, that means you can create a flavored oysters and things of that nature. So, this is in this application. So, this kind of why these type of innovation, even though while it started as a food safety, then the innovation enabled them to look at broader food safety and quality benefits. The other one is this beverages. So, a lot of beverages are kind of pressure treated. For example, if you visit Starbucks in the US, the pressure treated products, the juices and things like that, they are selling. So, one interesting thing with that is that if you have orange juice and pressure treated and try to sell this as a commodity product, it may not sell well, because the cost constraints, because people kind of very sensitive to price. On the other hand, when you have some of these specialty retailers where they are selling juices good for you, health, immune protection, those type of things, consumer willing to pay, and then you can able to pay that. So, a lot of the high pressure processed products introduced in the market today, these are all more what they call premium high quality product, where consumer do not mind paying the price, but not a commodity type applications like like a standard juice or milk and things of that nature. So, that is something needs to consider. And here we can see here different type of products categories being processed in the market, and these are just examples of products available in the US. Pressure treated products are also available in Europe, Australia, China, India. So, India has a number of juices and other products in the market. Again, what I heard is that there is more and more food processors in India are interested in to get into the high pressure processing. The pressure assisted thermal sterilization or high pressure sterilization, you take the food, package it, and then you are going to preheat to certain initial temperatures. So, 70 or 90 Celsius, and then you are going to pressure treat at so that the product temperature reaches 120 Celsius. So, you can inactivate spores, including the Clostridium botulinum, and you can also achieve enzyme inactivation, and you can able to achieve commercially sterile products, like for example, you can make stews, soups, coffee, tea, flavor, and many products like this. And FDA issued no objection for industrial petitions during the fast 5 years. There was one in 2009, there's another one around 2014. One is mashed potato, another is what I call seafood type product. As of now, there are no commercial products in the market, but I think there's a lot of research activities going on, so that eventually you will see commercial application in the market. Now, if you are hearing about high pressure processing first time, you may ask the question, is the high pressure processing, you are talking extreme level of pressures, will this crush the food? So, for example, I have a carrot, pressure treated, is this going to smash it? I think the answer is no. The reason is there's a difference between shear pressure and high pressure. So, the high pressure, the pressure application is isostatic, so it's applied uniformly all around the product. So, to illustrate the concept, let's think about this. If you take a piece of grape and put between your fingers and you're going to squeeze them, you will see that you are going to squeeze, apply some pressure, but that pressure is a shear, so that you're going to damage the grape and it's going to burst open. On the other hand, you take the grape, maybe take a container like this, put the grape inside, fill with water, and then squeeze the container. You are going to apply isostatic pressure. The water pressure is going to transfer all around the grape. So, it's similar thing happen inside the pressure vessel. So, this is why if you look at this fruit before and after processing, they look very similar, but they are placed inside a water medium, so that they don't get crushed. On the other hand, look at this guy here. This is a styrofoam cup. It pressure treatment, it significantly lose lot of the volume, because all the air in the system was removed. Once the pressure removed, it cannot go back. So, as a result, if you have a leafy green, any fruits and vegetables have lot of air packets. These are all not very good candidates for pressure treatment, but otherwise meat, seafood, almost any different varieties of food products can be pressure treated. The principle behind high pressure processing are the following: isostatic pressure. Basically, what it says is pressure is transmitted uniformly instantaneously throughout the sample, and process time is independent of sample volume. So, what that means is, if I have a small say carrot piece versus a big say chicken breast, smaller carrot piece can be cooked quite easily because it is a small size, whereas it may take longer to cook chicken or other meat products, because the size is going to take longer to cook. Whereas, in the case of high pressure processing, both going to take the same amount of time, because the pressure is applied uniformly volumetrically throughout the sample, and you can able to take it effect. The second is the Le Chatelier principle. It kind of says that any process observed with a reduction in volume is favored by increase in pressure. So, there are chemical reactions, there may be volume increase reaction, there are reactions with volume decrease reactions. So, a reduction in volume going to be favored by pressure treatment. Organist relationship. So, this is one of the things scientifically pay attention. People claim high pressure processing non-thermal technology, but strictly scientifically speaking, pressure treatment is a thermal process, because you are always going to have a thermal component associated with the pressure treatment, but the extent of thermal increase is significantly low, so that you can probably ignore that thermal effect. So, that means you have to consider the organist type relationship, so that some of the thermal dependency of the reactions. The pressure treatment affect the non-covalent bonds. It has a limited effect on low molecular molecules like flavor, aroma, pigments. So, that is why pressure treatment products looks much more naturally looking, fresh, tasting type of thing. And you probably do not destroy vitamins, and it also inhibit Maillard reactions. So, there are reactions with the heat treatment, you can get a Maillard browning, those type of things. Pressure treatment does not do that. So, in other words, if that's a desired reaction for you, you have to use a heat treatment for that application. So, how the pressure treatment works? So, let us say I have want to process some vegetable cut slices or some meat products. You take them, package them, and then package that product inside a big canister. So, in other words, if you have a consumer size package, you load them in a maybe 100-liter basket, and that basket is going to be loaded inside a pressure vessel. So, you can look at the pressure vessel here. We will see a schematic come in later, but it has a pressure chamber, and then you have a closer in both sides, and then this is called yoke. So, this is kind of basically how the system looks like. Then what you are going to do is you are going to fill this with water. So, let us say that you have a 100-liter chamber, you are going to fill with water to up to 100 liters. There is no pressure change happens, but you keep pumping more and more water inside. So, maybe 200 liters, 500 liters, 600 liters, then it increases the pressure, and that is how you keep adding more and more water until it reaches 300 megapascal or 600 megapascal, and then you keep it for a certain time, and then you remove the water, and then you take the processed product out. So, one of the interesting thing is, since normally even in some of the engineering classes, we always assume water is incompressible fluid, but under these pressure conditions water is compressible. So, what that means is you take 1 liter water and you put it in the pressure machine, it is going to compress to 0.85 liters. So, that is about 15% reduction in volume, and then you are going to when you release the pressure, it goes back to the initial conditions. So, this is the schematic diagram for the equipment. It is kind of similar to what we saw, and you can see that this is the pressure vessel which is inside here, and then you are going to have the yoke which is kind of frame here, and then you are going to have the basket where loading unloading samples are here, and then you are also going to have closure. So, there is a chamber closer over there, and then you are going to have 2 pressure intensifiers, pressure pumps, and the pressure pumps use water as the pressure transfer fluid. Now, many of the lab units, pilot scale or bench scale, they use glycol or other oil type substances, and because it may be made with relatively inexpensive, whereas in the commercial industrial applications they always use water as the pressure transfer fluid. The pressure vessels, they can be made multiple ways. A simple thing is what they call a monoblock. So, this is the monoblock. You take a probably a forged cylinder, and that forms the cavity, and that you place the product inside, and then you pressure treat it. The problem is these probably going to break maybe after 1000 cycles or 2000 cycles, because you are going to develop stress cracks, and so that with the fatigue resistance and so on, you are going to break, and that is not reliable, because in food processing we do millions of cycles in an industrial level, day in day out. So, that means you need a better solution. The second option is a multi-layer vessel. So, multi-layer vessel is basically you have a monoblock, and then you can add another cylinder outside of that, so that you have 2 layers. It kind of improve the fatigue resistance, but still not the ideal one. So, what is currently industry practiced is what they call wire wound technology. Wire wound technology, basically they take pre-stressed stainless steel wire, and then they kind of miles and miles of that, and then form a big cavity by winding them here, and this way they can able to stress and then release the stress it can able to withstand those stresses even millions of cycles without any problem. So, this way this is kind of what commercially applied by all the equipment manufacturers. Then there are two types of pressurization. One is the direct pressurization, another is the external pressurization. So, the direct pressurization, imagine you have a product here and then you have a piston and then you use some type of driving mechanism to push the piston and then push, and you are going to generate pressure inside, and that causes the pressurization. And so, this is one type of application. We will see later on this concept may be used in ultra shear technology type concepts. The second is external pressurization. So, you have a pre-packaged product and then you put it in the pressure chamber, and then what you are doing is you are kind of adding more water, and then it is going to increase the pressure through that way. So, this is where more commercial batch high pressure equipment employ these concepts. The yoke also made of wire wound steel and frame, and you also have to have a process control and instrumentation, because these are all very high pressures. So, they have to monitor the pressure and then able to depressurize it when there is a need, all those things. So, that is where they have to use the process automation. The pressure pump, this is just an example how a pressure pump may look like, and it comes with different horsepowers, like for example 200 horsepowers, 200 HP, 50 HP or 1000 HP and so on, different values, and depending on how powerful your pump, you can able to achieve the pressure within that time frame. So, in other words, if I want to build the pressure in 30 seconds in a 100 liter chamber, you can do that if you use the appropriate pressure pump. On the other hand, a lot of the equipment vendors, they typically use about 2 minutes come up time for the pressure to reach 600 megapascal. So, that way they do not need to use very expensive horsepower pump, but they can use some moderate pump. And when initially started, a lot of the pressure machines were vertical orientation. What that means is they place the pressure chamber in a vertical room, and you are going to load the product inside and then you take the product outside. It is in the same environment. And what happened is, where many processing plants, you may have constraints with the vertical space, they may not have it. The second thing is, which is more important, is the product looks very similar before after treatment. So, it is possible a lay operator who does not know much about the science can misplace the process sample to unprocessed sample, accidentally unprocessed sample get into the process sample mix. So, this way now they are using a horizontal machine, so that they have one side say raw product side, the other side you have the processed product side. So, that means the operator this side know they have to load the raw product here, the processed product there is going to be collected. So, that way they can able to operate this much more cleaner way. The commercial equipments are about 600 liter capacity, and they can probably process about 20 to 40 million pounds per year. And now, this is a new technology. So, that means the cost kind of has been coming down, but relatively still expensive. Now, this estimate may be 1 to 5 cents rather than 3 to 10 cents, but still it is relatively expensive compared to a thermally processed product. So, that means that you still cannot use high pressure for commodity type product, but you can try to use it for value added product where consumer willing to pay for it. Packaging, you had to use flexible package. So, you cannot use metal cans, you cannot use glass bottles, but you can use pouches, because remember there is a reduction, volume reduction during high pressure processing, and this allow that reduction. So, you can use different things like trays, bottles, things of that nature, but it needs to withstand the pressure and temperature, the mechanical forces encountered during processing, and then you have to use the product with the high barrier pouch. Remember, when you are processing, you are modifying the properties of the food, you are also going to modify the properties of the polymer. So, in other words, if you are familiar with the packaging science, you have probably heard the term water vapor permeability as well as the oxygen transfer values, right. So, those parameters can be affected by pressure treatment. You may start with the high barrier properties, and then after pressure treatment those barrier properties lost. So, what that means is you may start with a high value ordered product with superior quality, but you are storing the product in a package which has insignificant barrier property. So, you are going to lose your property, your quality benefits over storage. So, that is why it is always important to have proper packaging. So, this is just showing you have the oxygen transmission property for certain material, and then how the pressure treatment going to keep it without any damage. I think the figure did not come out very well. If you need, I can show you the picture. This is also published in this paper here, so you can probably get the image there. But the essential data here is pressure treatment can modify the barrier properties. So, if you have to use the proper packaging material to select the maintain the barrier properties. Let us look at the microbiological criteria. So, normally we have used thermal processing, and thermal processing we looked at the microbiology over last 150 years. So, we know how to make products safe. Now, high pressure processing use pressure. So, what type of criteria you need to establish? So, what type of pathogen do you choose? So, is pathogen in a thermal process going to be pathogen in high pressure product? In other words, let us say you are taking E. coli 157 is one of the more resistant for heat treatment. Is that going to be more resistant for pressure treatment, or pressure treatment going to be easily inactivate them? So, those are the type of things. So, what you need to do is kind of first look at the most resistant pathogen of public concern survive the process. So, if you are processing meat products, what are the outbreaks? So, is that E. coli outbreak, or is it Listeria caused the outbreak, or is the Clostridium caused the outbreak? So, you kind of gather that information and then see how much inactivation you need, and you also need to consider the injury and recovery. Remember, pressure treatment is a relatively milder form of treatment. So, that means bacteria may appear dead, but they are really injured. So, with the right growth media they will come back, and a lot of times food is a good nutritious medium. So, they may grow back. So, you have to consider that as well. And then you also need to consider the protective effect of composition, pH, water activity, similar to what we talked earlier, and then you have to validate the process. So, again, if you are a student of microbiology, you know that there is no one single Listeria, there may be thousands of Listeria there. So, somebody has done a study where they looked at 100 different type of Listeria, and what they found is some strains they had 0 log reduction, some strains they had 6.75 log reduction, some strains they had probably about 3 log reduction. Now, imagine yourself as the manager who needs to decide the safety of high pressure processing. Which one of the strains do you choose? I will give you 3 choices: 1, 2, 3. Do you choose 1? You probably do not choose 1 because there is no log reduction. So, if you choose that, you are going to say high pressure is not commercially viable, but millions of products are commercially processed. So, how do they manage to do that? If you choose 3, you are going to say I am going to get log reduction, 6.75 log reduction, but you may have lot of more resistant spores or bacteria survive, so you may get outbreak. So, the point of the matter is you do not take number 2 either. So, what you have to do is, let us say you have a high pressure processing plant in say Ranchi, then you look at in the neighboring states, and let us suppose you are processing vegetable products. So, you can say, okay, over the last 50 years, 100 years, what type of outbreak happened in vegetable products in around this place where I am going to get my raw material, what type of pathogens there, and then you take those pathogens and do the study, make sure you can inactivate them. Because one of the common mistake people do is they look at the published literature and then they try to mimic that for their process, but that may not guarantee the safety, because the published literature may be different resistant than the bacteria found in your area. So, you have to kind of pay attention, and this is I am illustrating with the high pressure processing, but this may be true for many non-thermal technologies like pulse electric, UV and other processing technologies. Another thing you need to consider, when you apply high pressure, there is going to be some temperature increase. So, that means you are going to apply both temperature and pressure during treatment. So, how do you consider that? So, in this study we looked at a chemical marker called M2 marker with a whey protein gel, and first we did this heat treatment 105 Celsius and say about 5 minutes, and then you can see that the marker yield increased with increase in holding time. So, this is primarily heat treatment. The next we have done is pressure treatment at 30 Celsius. You can see that the same gel, you do not have formal pressure treatment, because pressure kind of inhibit that reaction. So, you have decrease. When you have 700 megapascal, slightly similar thing. What if I increase the temperature to 105 degrees Celsius? You can see that marker yield is increasing. So, in other words, you have two forces acting on it. One is the heat, which probably in this case favor the reaction formation of the chemical. The other is pressure, which is antagonistic. So, it is kind of inhibit the formation. What you see is the net result of that. So, when you do high pressure processing, especially with the combination of high pressure and temperature, you have to consider both thermal effect as well as the pressure effect. So, to illustrate the point, we looked at the Bacillus cereus spores in cooked rice, and you can see that when I have just the thermal process at 85 degrees Celsius, it takes almost 160 minutes. It is almost like 3 hours to get certain log reduction. So, 7-8 log reduction. But if you are doing only 60 Celsius, you can achieve the same in about 7 minutes, or if you go to 85 degrees Celsius, you can even achieve in about 4 minutes. So, you can see that pressure and temperature can synergistically inactivate the bacteria as well as some of the other chemical compounds. Here we are looking at the inactivation of one of the pressure resistant spores called Bacillus amyloliquefaciens. So, it is one of the pressure resistant spores, and the point I am trying to make here is you have the log reduction versus temperature, the log reduction versus pressure. What you see here is at 0.1 megapascal at a lower temperatures, you can see that the log D values are much higher, whereas for pressure treatment these are much lower. So, this means there is an enhanced pressure lethality, whereas as you increase the temperature at 120 degrees C, they kind of clump together. So, that means pressure, if you operate the pressure vessel at 120 Celsius, it becomes like an expensive autoclave, because there is no contribution of pressure lethality, it is primarily coming from heat. Temperature become dominant factor. So, then we kind of went and did a mathematical model where we looked at the D and Z values for the bacteria from pressure treatment. We also looked at the D and Z value for the bacteria for the thermal processing, and then we integrate them. And let me kind of explain here. So, this is 600 megapascal 103 Celsius for 5 minutes. So, this is thermal only lethality, whereas this is kind of combined pressure and thermal lethality. You can see that at that conditions you have a more lethal effect due to pressure and temperature, almost negligible effect only with the heat. Now, if you could increase the temperature to 600 megapascal 116 Celsius, you can see this is the pressure thermal lethality, this is thermal only lethality. So, they are kind of coming close together. If I do this at 121 Celsius, you can see that those two will become same. So, because the temperature lethality become a dominant factor, pressure does not have any lethal effect. So, you have to kind of consider some of those things together. In terms of shelf life, high pressure processing extend the shelf life. So, for example, if you have orange juice 8 days versus 120 days, if you have hummus about 80 days, salsa 15 versus 120 days. So, you can see that quite significant extent of shelf life. From a consumer point of view, they may not find this benefit, because sometimes consumer expect things to spoil in couple of weeks in the refrigeration, but it gives the opportunity for food processor to distribute for longer distance. So, for example, you make hummus in say Cuttack, you can probably send to, for example, south of Kerala or Kashmir, or you can probably export to Europe or US and so on, because that kind of provides the longer shelf life, help you to send to a wide geographical distances. Enzyme inactivation, as mentioned, pressure is not very good with the enzymes. The efficacy varies based on the type of enzyme, pressure level, time, pH, temperature. So, a simple solution is, if you want to pasteurize product with high pressure, you do thermal blanching followed by high pressure processing. That way it takes care of the enzyme with heat, and then you take care of the microbes with the pressure treatment. Now, some nutritional things here. Pressure is also helpful to protect ascorbic acid. So, here you can see that pressure treatment with ascorbic acid, it kind of retained everything together. On the other hand, if you look at thermal processing at a different temperature, you can see a degradation with a certain time, and then if you have a combination of pressure and temperature, you still have a degradation of ascorbic acid. So, in other words, pressure treatment at chilled condition reasonably or mostly protect most of the nutrients. On the other hand, when you start adding heat to it, it is going to probably degrade to the extent how much heat you are adding to the system. This is just to look at the furan formation, because there is a concern with high temperature furan can be formed, and that can be a healthy concern. So, we kind of looked at thermal processing, and then PATP is pressure assisted thermal processing, HPP high pressure processing. What you see here is the heat always going to form some furan in different type of juices. On the other hand, the HPP, it kind of forms below detection level. Now, I think I also want to acknowledge that even though these levels shown here are high, but from a regulatory point of view, they are still within the threshold, so that they are safe to consume. But nevertheless, with the increased detection efficiency of various analytical techniques, sometimes consumers want to know what compounds formed, how they can be controlled during processing, and so on. So, this is kind of provide pressure temperature history during high pressure processing. So, for example, you may have a product at certain initial temperature and then you kind of equilibrate it, and then you are going to load inside the pressure vessel, and then you are building the pressure, and then you are holding the pressure, and then you are going to depressurize it. So, during the time you can see that there is a temperature increase and then it is maintained, and then when you remove the pressure, the temperature falls down. So, what is happening here? So, remember I talked earlier, when you are compressing the material, the liquid is going to compress, or the even the substance is going to compress 10-15%. So, when you compress the material together, the molecules coming together, that means they have increased opportunity for friction, and that friction shows us the temperature during pressure treatment. And then it is maintained as long as you maintain the pressure. When you remove the pressure, then the molecules, the substance go back to its original volume. So, that means no longer they have opportunity for increased friction. So, the temperatures kind of goes back. So, this kind of is called heat of compression, and we have kind of determined the heat of compression for different substances. So, to illustrate the point, we have done some experiments where we looked at water, skim milk, vegetable oil and different products. And you are treating 300 megapascal 25 degrees Celsius. So, this is 25 degrees Celsius, 300 megapascal, you increase the temperature, it kind of comes down. So, you can see the temperature increase is about maybe 12 degrees Celsius. Look at vegetable oil, you can see that it starts 25 degrees Celsius, it goes close to 47 Celsius. So, what happened? Both water, milk, everything start at same temperature, but why oil kind of goes much higher temperature? The reason is depends on the polarity. If you look at water, these are polar molecules, that means these are oily compact molecules. So, when you compress, you can compress only so much, whereas if you look at lipids, they are non-polar, long chain molecules or short chain molecules. So, that means you compress, they are going to compress certain way, give out some heat and then try to be stabilized there, and then you further compress, it is going to keep compressing, and each time it is going to give out some heat. So, that is why there is a significant temperature increase during the fats and oil. So, as a result, you can able to document the temperature increase depending on different substances as well as the initial temperature. Normally, in the literature used here, there is a 3 degree temperature increase per 100 megapascal pressure, that is done at 25 degrees Celsius, whereas if you do chill condition, the temperature increase even less, it is about 1 degree Celsius, whereas if you have a 70 degrees Celsius, you may get about 5 or 6 degrees temperature increase in water. And if you look at fats and oil, they have about 6 to 9 degree temperature increase under these conditions. You also need to pay attention to the technology limitations, because non-thermal technology like high pressure do not inactivate spore. So, you have to combine with heat to make them safe, and when the water activity is very low, high pressure is not good. It requires some water, so that it is effective against the bacteria. And if you have air packets, again it is not good with the pressure treatment as well as PEF. It kind of provides look at this. And when you have light based technologies, you have to consider the shadowing, and many of the non-thermal technologies, they have a high cost of equipment. So, that is something needs to consider. And one of the limitation of non-thermal technologies, or at least it is not thoroughly researched, because today there is also a lot of concern about presence of heavy metals, pesticide residues in fruits and vegetables and products. Pressure treatment is effective in inactivating bacteria, but not necessarily their efficacy against the heavy metals and pesticide residue is not known. So, that needs to be looked at in the future. Other interesting thing is in the US, with the success of high pressure treatment, there were a lot of copycats. What that means is, for example, like high pressure processing, people selling juices. So, instead of subjecting them to 600 megapascal pressure, they were subjecting them, 600 megapascal pressure is about 87,000 pounds per square inch, but they were applying 100 psi pressure or 200 psi pressure. So, this is like a juice pressing equipment, and then they were selling this as a high pressure processed juice. From a consumer point of view, they do not know what is the difference between pressing the juice or subjecting to a high pressure processing. So, the industry then formed a logo, so that they said anybody who is properly treating high pressure with certain proper conditions, they can use the logo. Anybody just using only 50, 10 psi, 100 psi type of thing, they probably may not able to use this logo. So, this way they kind of try to build a safety mechanism against people trying to make money quickly without doing the proper scientific work. So, take home message is pressure is a fundamental thermodynamic variable. It has a very versatile applications. We initially pressure started as a food safety technology. Today, it is used in wide range of applications, and in addition to pressure treatment in food applications, it has applications in cosmetic, pharmaceutical and medicine, because for example, you can create vaccines, or you can develop some novel cosmetic from food ingredients with these type of things. Now, I am going to talk in the next couple of slides ultra shear technology, which is basically a continuous version of high pressure processing. Remember, food industry always interested in continuous version of the technology rather than the batch version, so that it helps to improve the productivity. And this is where the high pressure processing come in. So, the concept simply illustrated here. You have a raw juice here, and it is sent to a pressure chamber treated 400 megapascal. So, remember here the juice is not packaged, it is just the whole liquid is here, and then you are going to discharge through a shear valve, so that the pressure is relieved, and then the product comes out here as the treated product. How it works in a pilot unit here. So, you have a treated product, and the product is pumped inside the flexible tubing. So, what this vision has done is they put two flexible tubing inside the pressure chamber. So, the product stays inside here, the pressure transfer fluid is kind of passed through the annular space. So, they squeeze the tube, pressurize, and then when you remove the pressure, it kind of retains. So, after you remove the pressure, it goes through a shear valve where the pressure is discharged, and then it goes through a holding tube, cooling heat exchanger, and then aseptic filling. If you look at this section, you probably see the holding tube, cooling section, and then aseptic packaging. You probably see them in the aseptic processing as well. So, essentially ultra shear technology kind of merges pressure technology, which is a non-thermal, to the pressure thermal based technology. So, it is a hybrid thermal non-thermal technology. So, this can help with the making clean label dairy plant protein beverages. It can also use as a green extraction technology. It has applications in variety of industries as well. So, you have questions?
Where is the thermal part in the
Okay, so the thermal part comes after it passed through the shear valve. So, when the product comes out the shear valve, there is a significant temperature increase. There is a 20 Celsius temperature increase for 100 megapascal. So, if you apply 400 megapascal, you are going to have 80 Celsius temperature increase. So then you have a whole tube, and then you have the cooling section and so on. So I will come to that in the next couple of slides. Other questions?
So the pressure comes in the picture first and later is the
So pressure comes in, you pressurize it, then you are getting into the pressure, they depressurize it, and when you depressurize, there's a significant temperature increase, then the sample can be considered as a thermally processed sample, and then the existing thermal process regulation potentially used to may demonstrate the safety. So the level of shear happening during the high pressure shear is about 10 power 7. So normally in the standard shear it may be 10 power 2, 10 power 3, here it's 10 power 7. So that's why there's a significant temperature increase happening. So to illustrate the point, here there's a temperature increase 3 Celsius per 100 megapascal during isostatic pressure processing. So this temperature increase we're going to go back when you remove the pressure. Whereas you can see here 18 degrees temperature increase per 100 megapascal during ultra shear technology. This is permanent, that means you have to use external cooling to remove that heat. So that's kind of the two difference between the batch high pressure processing, also the high pressure homogenization, and the process. So let me kind of try to come here. So what we have done is we use this concept to pasteurize or sterilize products. Let's suppose I take a juice, I process with 5 degrees Celsius initial temperature, and let's say I treat 400 Celsius, and so that means 5. Let's, for the purpose of calculation, I'm going to make this as 400 times 18 by 100. So 5 plus so approximately 77 Celsius. So you can see this is kind of similar to pasteurization temperature, and you can probably use existing pasteurization temperature to get this passed through the regulatory authority, because in the holding tube the product going to spend enough time what you have in thermally pasteurized product. Now if you look at other side, let's suppose I take 75 degrees Celsius initial temperature of my product. So that means I have to heat my product, then I am applying 400 megapascal pressure, and then again this 18 degrees Celsius temperature increase. So 147. So you can see that this is kind of getting in the neighborhood of USG treatment of milk or any products. So that means you can do USG, make a self-stable product under this condition. So simply manipulating the initial temperature and the applied pressure, proper shear valve, you can pasteurize or sterilize food products using this approach. One of the interesting thing with the ultra shear technology is that it kind of shifts the particle size much shorter, lower end compared to the regular thing. So you can see the untreated milk is probably somewhere this blue line here, whereas high pressure processing also somewhere in this cluster, whereas the ultra shear technology shift quite a bit in the lower end. So you can be able to have much finer particles. And this is a particle shift in tomato juice. So you can see that control versus the USG, control versus thermal processing, control versus HPP. So essentially control, thermal processing, HPP, they have a similar, whereas USG shift the particle towards the lower end. And what we found also, depending on the type of material, the shift probably not going to be infinite. So, maybe up to 160 megapascal there is a decrease in particle size, then you are going to start aggregating. So, what we found is you may have to add a secondary shear valve, so that you can remove that, so that you can still maintain the particle size. Another interesting thing is pressure, temperature can combine, so that it can significantly modify the rheological properties. I know it is a busy slide, but let me kind of try to convey here. We took milk, pea protein, and then we had different combinations, like for example 1:0.5, 1:3, and then we were treating with pressure, high pressure, ultra shear technology, and then we are also doing traditional homogenization, which is like 3000 psi. What we found is normally pressure treatment, thermal processing, the particle size doesn't or the viscosity doesn't significantly increase. This is the traditional homogenization, whereas you can see here this is the ultra shear technology. It significantly increased. What that means is you can start with a liquid, say milk and pea protein beverage, and then by proper conditions of pressure, temperature, you can have a beverage, the output may be a liquid, or you can have a sauce, you may have a thickened beverage type thing, or you can have a gel which is much more thicker. So, it can modify the viscosity properties quite a bit. So, it kind of creates a lot of new structural applications with various food processing applications with this ultra shear technology. And you can see that how the particle size can be significantly reduced. You can see the untreated particles, raw milk and protein versus the UST treatment, whereas if you have a cream and pea protein, you can see much thicker gel can be created. One of the questions we always had is, you had different non-thermal technologies. The industry always asks us, which one do you choose? I think some of you asked the question, which technology to choose, and the answer is it depends on various factors. But from a nutrition point of view, we wanted to see how different non-thermal technologies affect the nutrition. So, we took beetroot juice, and then we thermally process them, high pressure process them, ultra shear technology process them, and then use the NMR to analyze different components present in this. So, you can see lectin, there are different components, valine, glutamine, alanine, and so on. So, there are so many different things the NMR can differentiate. And then you can see this is the unprocessed sample, and you can able to separate different treatments. So, I believe this is the this is the HPP. You can see it is relatively close to thermal, and then thermal had more degradation, and then ultra shear technology has the next more degradation. So, in other words, if you look at batch high pressure processing, it is primarily thermal processing. So, so you have thermal processing kind of degrade more nutrients, whereas ultra shear technology has less degradation, and then the pressure treatment has the least. And you can see that sensitivity changes for different things. So, here heat destroy more of them, whereas HPP and USG retain more. So, in other words, you can also now have another tool where you can probably look at the metabolomic analysis as well as the microbiological analysis. Then you can get a comprehensive picture. What is the impact on my microorganisms? What is the impact on my nutrients? So, this is more shear sensitive product. So, I may use this technology, whereas this is a more heat sensitive product. I may use this technology, and so on. So, you can kind of, rather than blindly selecting technology, you can probably try to build in some scientific rationale behind your choice. So, ultra shear technology is an hybrid technology which combines pressure and non-thermal, and there are variety of clean labeled beverages can be processed, emulsions can be created because you have a significant particle size reduction, rheological characteristics and stability all there, and then you are going to have diverse product applications. At the moment the technology is not commercial, but I think in the coming years we expect the technology to get this commercial. At the moment we have some companies working to commercialize certain nano emulsion type products. So, here are some selected readings, and we can have some discussions.
Good morning. I wanted to know currently what your lab is, what is the focus of your lab right now with high pressure processing? What are they working on right now?
So, one of the things right now we are looking at is we are looking at different technologies, how that affects the nutrition. So, I think so I saw show the results from beetroot, but since then we were processing number of other fruit juices, and then we were comparing how different technologies, thermal, ultra shear technology and HPP affect the degradation of the nutrients. So, a little bit focus on metabolomics, but lot of those things are driven by industrial interests and applications. So, there is also interest in PATP, pressure assisted thermal processing as well. So,
Sure. So, what are the parameters that are being monitored when these technologies are put to use? Like when a product is getting high pressure, what are the parameters that are being monitored?
Sure. So, for high pressure pasteurization, pressure, temperature and time, these are the three parameters. So, in other words, normally I keep saying pressure, temperature and time. Now, we add high pressure, temperature and time, even though the industry get around temperature by putting the pressure vessel inside a refrigerated space. So, when you have a refrigerated space, you do not need to monitor, control the temperature, you just only focus on monitoring the high pressure and processing time.
Sure. What I was trying to ask is that the quality of the product. What are the product qualities that are being monitored while the product is going through high pressure processing?
So, after high pressure processing,
yes,
the product is evaluated same as anything we do not today in food science or thermal processing of products, right. You look at the texture, look at the color, you look at the nutrition, look at the microbiological safety, and whatever normally you do, you probably take care of those things.
Okay. Sure. Thank you.
Sir, I have only two technical questions. Since in case of like proteins, sulfur containing amino acid and aromatic amino acid, that can be easily oxidized. Can you give any idea how it will behave when HPP will be applied?
So, what type of product?
And in protein, there is a mostly aromatic amino acid groups and sulfur containing amino acid. If we use any technology, these are the most sensitive amino acids. It can be easily oxidized, degrade, into convert into any other form. Can you have any idea how it will behave when we applied HPP?
Yeah, I do not know the specific compounds. So, probably either I have to look at the literature, somebody has done it, or new studies needs to be performed.
And second one is, you told us like HPP reduce the particle size. In large scale operation,
not HPP, the ultra shear technology.
Okay, sir, yes. So why not they are using ultrasonication? It is mostly effective to reduce the particle size.
Right.
It's
So remember, there is no comparison between technologies.
Yeah.
Each you have different tools. It's up to the process to use the different tools, right? So each one has a unique strength and weakness. Then some products may be helpful for certain things, some help the others, and so on. So like if you look at ultra shade technology, PEF, UV, so these are all can be used with the liquid products, and you can also use the warm heating for in terms of pasteurization, sterilization. So you have a gamut of tools available. Which one do you need to use for a specific thing? I think it's up to the food processor, their goals and their resource availability, all those things.
Sir, to prevent the aggregation, is the industry people adding any additives to prevent the aggregate of the particles? Since ultrasound technology reduce the particle, it has a tendency to agglomerate together. Maybe if so, is there any kind of additive they are commercially available that can be used to prevent this agglomeration?
So again, what we are reporting is a research results. So it's not industrially practiced. That's number one. So the goal at the time was look at clean label. So what we are trying to do is we are not trying to do anything additives. We want to do everything only with processing. So that means pressure, temperature, shear. So we are not adding any additives, any of those things. Now, when it goes to industrial practice, I'm sure they're probably going to use a combination of processing and additives, so that they can probably achieve. And some of the additives potentially could be more natural additives rather than synthetic additives, so that they can maintain the clean label type status.
Okay, thank you, sir.
Would you like to take a break or?
Yes, sir. 5 minutes.
Okay, so the next one we are going to talk about is the pulse electric field processing. And pulse electric field processing is similar to high pressure in the sense it uses a non-thermal variable, which is electric field. In the high pressure processing, we were using very extreme pressures. In the pulse electric field processing, we are using very high voltage, like it's the 35 to 50 kilovolt per centimeter type application. So you take that very high burst of high voltage, 30 to 50 kilovolt per centimeter, and then apply them on your juice product in nanoseconds. So, that you apply pulse in nanosecond, then you pass it for a certain time, apply and then remove, apply, remove, and so on. So, it is not continuous. In the case of Omi heating, you are applying very low voltage and then you are continuously applying the voltage during passage of current, whereas here you are just exposing the voltage and very short pulses. And the treatment time can be very short, it is so many seconds, and it is a non-thermal method of preservation. So, the origin of PEF comes from some of the work done in 18th, 19th century by some scientists, where they want to look at the effect of electricity on biological tissues, and then they were kind of developing some models to describe how electrical pulses permeabilize the cell membrane. And other thing is the high pressure technology also, sorry, the PEF technology came from Cold War, right. I think US Army had companies, Maxwell and Pure Pulse, number of other companies related to defense applications. When the Cold War ended, they were looking for non-defense applications, and that is where some of these new processing technologies kind of emerge. PEF is one of them. The PEF has potential application in juices, syrups, emulsion, ingredients, and original concept they had in mind was pasteurization, and even today not much research is done. So, the spore inactivation is not well characterized, so not much known, but in theory based on the other technologies we know when you combine PEF with heat, it is possible to sterilize the spores, but the data is probably not available. You can also do the extraction type applications as well. Simply stating, you have your source of energy and you store the energy in a capacitor inductor circuit, and then through a switch you are going to release the energy suddenly, and that is expose the product in the treatment chamber, and then you repeat this number of times. How that look like in an industrial scale? So, you have for example, your raw material tank where you may have a juice or milk, and then you are going to preheat to certain temperature. Lot of times you are adding a preheater, basically you are kind of bringing everything same uniform temperature. So, it may be 5 degrees Celsius, it may be 50 Celsius, or it may be 70 Celsius, but you kind of bring an uniform temperature. Then it goes to the treatment chamber, and then between treatment chamber you have a cooler. Why? We will talk about that a little later, but remember pulse electric field uses electrical energy, and you are using very high, a lot of electrical energy delivered to the product in a very short time. So, there is going to be some significant temperature increase after PEF treatment, and we want to consider this as a non-thermal. So, that means they want to bring the temperature down below certain target level. So, they added a chiller after each treatment chamber. So, you can bring the thing down. Now, from the US perspective, this is one of the reasons PEF probably not picked up from a commercial interest, because PEF itself energy intensive, to that you are adding chillers which also takes energy and so on. So, they kind of looked at this energy intensive process, whereas later on we will see PEF as a pasteurization technology became more commercially practiced in Europe, but not in the US, where high pressure probably become more a technology of choice. So, you can see different countries or different parts of the globe prefer adapt different technologies based on the local industrial needs, and then the local preference from the consumers as well as the industry and other sources. So, this is just to show you how a large industrial scale PEF equipment, it can process for example 100 tons of a product per hour. So, the key components of PEF are a power supply, a pulse modulator which is like a capacitor inductor circuit, and then you have treatment chamber where the treatment is kind of applied. So, the product goes in and then product comes out, and then you have the electrodes, high voltage electrodes, and then the treatment zones are here where the product receives the proper treatment. Now, when you look at thermal processing versus PEF, PEF has some different number of process parameters. You know, when you looked at process parameters, you need to control for thermal, its pressure and temperature. Then we said high pressure processing, set high pressure, temperature and time, and then they overcome that temperature by putting in a chilled room. What is PEF? Here you have much more variables, you have field strength, repetition. So, in other words, how many pulses you apply per second? Is it 1 pulse, you apply 10 pulse, 100 pulse, and waveform. So, if the pulse is applied like a square wave, or you want to have exponentially decay, or you have what I call kind of both positive and negative. So, you can have different waveforms possible. So, this is more related to the electrical engineering aspect of creating pulse and delivering the pulse, but there is opportunity there, and then the temperature and so on. So, obviously, this list is much more bigger. So, that means you do not have any more simple saying, okay, control temperature, control time, you are done. Now, you have to bring in a computer and the computer monitor various things, and then that makes the decision whether the process is safe or not. So, it is going to be limit complex. The D and Z values, you have a constant temperature, time, you can develop D value, Z value from that. Whereas, in the case of PEF, with all these different parameters, these parameters become much more complex as well. So, these are all still evolving. On the other hand, PEF can be both continuous, but it can be done as a batch process as well, but primarily continuous. Thermal can be primarily batch and continuous. One of the limitation of PEF is you cannot do particles, because when you deliver the pulse, it has to be delivered on a juice or liquid, whereas when you have a particle, it is going to interference with the delivery of the pulse. So, you probably normally do not do that, and then the clearance of your chamber, this is probably couple of millimeter size, because the smaller the electrode gap is, you can have much more uniform electric field distribution. If you have a larger electrode, you are going to have a wide range in electrical field distribution. When you have wide range of thing, the treatment may not be effective. So, you have to kind of control that. There are many physical changes with thermal processing, whereas PEF probably none. PEF does not do enzyme inactivation. You can do pasteurized in both cases. Sterilization probably is not much research has been done. So, the process parameters, probably we talked earlier, field strength, treatment time, pulse width, pulse polarity. You can see here different type of polarity pulses, square wave, exponential decay, oscillatory pulse, and so on. You also need to consider the electrical conductivity, pH, and water activity as well. So, here it just to highlight how temperature influence during treatment. It is a function of the electric field, treatment time, the conductivity, the specific heat. And you can also see that when you apply single pulse continuously without cooling, after each pulse there is a temperature increase, and that means suddenly the temperature goes away above certain critical value. Let us say you have a juice and you have a heat sensitive ingredient where you do not want the temperature exceed 60 Celsius. Then the temperature exceeds, then you probably go into degradation of that juice. So, to avoid that, what they have done is added chiller. So, after each pulse you cool down, heat it, cool down, heat it. So, this way you have much more non-thermal technology can be maintained. The PF design is influenced by how much flow rate you can have is based on what type of power system, PF power system you have. The diameter of pipe you have is going to govern what type of voltage you have and so on. So, the smaller the diameter, you are probably going to have a better high voltage, whereas if you increase the distance, you are going to lose that or non-uniform voltage distribution. People have looked at combining PF with ultrasound, temperature, chemicals, bacteriocin, high pressure. What they found, for example, high pressure PF does not work together, they work antagonistically. So, in other words, there is no benefit of combining PF and high pressure, but there is a benefit of combining PF and temperature, there is a benefit of combining PF and some of the chemicals, antimicrobial agents or niacin, bacteriocins and so on. And this can be done simultaneously or sequentially. What that means is, maybe you can probably preheat the material and then do the PF treatment, or you can do the heating and preheating do the PF treatment same time. So, it can kind of look at it and then you have to control things accordingly. So, microbial resistance, bacterial spores or bacteria tend to have higher resistance than yeast. Gram positive organisms, remember like Listeria monocytogenes, they have more resistance than gram negative, remember like E. coli type organisms. Spore formers, they are more resistant than vegetative bacteria. So, that is why still PF is not investigated for sterilization. So, pasteurization is kind of very known, whereas spores by itself cannot be inactivated by PEF. So, more research is needed. There was one publication which claimed PEF can be inactivating spores at room temperature, but the results were not reconfirmed. So, that is why it is kind of still more research is needed. So, what happens during PEF treatment? Let us think about OMI heating. You have two electrodes, you have a microbe and then you apply very low voltage. You are going to pass electricity through this and then the cell is heated and then it is going to die. Now, you increase the voltage to 10 to 20 kilovolt per centimeter, you apply the voltage, you are going to create some spores, it is called electroporation. So, you create a hole and in gene editing or some of the biotechnology applications, you can insert some beneficial modify the bacteria and so on and so forth. And then when you remove the electric field, the membrane kind of closes, so that you kind of function. So, that is a moderate voltage. In the case of PEF, you are going to open like electroporation, but it is irreversible. In other words, the cell is going to stretch so thin, it is going to break and then it is going to die. The content is going to come out and the cell death is going to happen. So, there is a critical voltage for this. So, that means E. coli has a certain critical voltage, Listeria may be a certain critical voltage. So, in other words, E. coli start dying maybe at 25 kilovolt per centimeter, Listeria may be a little more resistant, it may be start dying maybe at 30-35 kilovolt per centimeter and so on. So, that is something you need to pay attention to. So, what is the mechanism of cell death? You know, bacteria kind of surrounded by water, and when you apply the electric field, the water is going to influx, it comes in, and then the water inside content is going to go out, and then you are going to have cell death accordingly. So, that is kind of what probably at least the current understanding is through the electroporation and then damage the cell membrane and releasing the cell content. It is possible you can also have a injury. So, in other words, if you look at this, you get complete inactivation, whereas if you have intermediate application of PEF, rather than going 50 kilovolt per centimeter, instead of maybe 30 kilovolt or 25 kV per centimeter, you can have sublethal injured, so that there may be some death, and then the bacteria can able to come back and grow. So, that is something also need to be considered. PEF is electrical based technology. So, that means the conductivity probably something needs to be considered, and you do not want to have any particulates in your PEF system, and then the pH is something needs to be considered. It works well with the acidic product. So, that means if the pH is adjusted to acidic, it works well, whereas the low acid product, it does not work very well, because in low acid product you may have bacterial spores survive, and PEF is not good in activating spores. So, that is kind of why you kind of want to avoid. The other thing you need to consider when you apply PEF, there is a temperature increase that can probably lead to flavor, color, protein coagulation, nutritional changes, all those things. So, those things also consider. The electrical conductivity, we saw the electrical resistivity or conductivity probably measured in this case millisiemens per centimeter. You have again different products have different values. So, this is something needs to be understood before you get into the PEF. So, PEF, when they demonstrate in the lab, they have demonstrated with a lot of the high acid products, whereas they have less success with the low acid products. And you also have a protein coagulation may take place because of the high voltage, create a high temperature, then you have a protein deposits in the electrode, and that result in non-uniform field and treatments, and that can cause some difficulties as well. So, you also need to look at the voltage gradient or the electrical field distribution between anode cathode. Is this much more uniform, or is there going to be some gradient voltage non-uniform distribution? Then you have to consider that as well. Now, when you have, for example, you are treating milk, milk has, it is like a protein, it has water, it has a fat particles. So, fat is a poor conductor of electric field. So, that means it does not go inside. So, it try to bypass this way. So, that means if you have multiple fat particles, you are not properly homogenized, you can probably create uneven treatment. So, that is something needs to pay attention to. If you have a air packets, like remember we talked about in the case of aseptic processing, high pressure processing, it is also true for PEF. When you have air packets, when the electric field try to go through air packet like an insulator, and when the electricity or electric field hits, you are going to get a big noise. It is called a dielectric breakdown, and as a result you may get a arcing, and it may shut down the equipment, all those things. So, the best thing to do is when you have a raw juice, you add a vacuum step or de-aeration. So, remove the air bubbles, so that you can have much more effective treatment. One other thing you need to consider when you look at non-thermal technologies, high pressure, PEF, UV and many other things, these are minimal technologies and you want to preserve the quality. So, in the interest of preserving quality, sometimes processors want to choose less and less minimum treatment, so that they better preserve the quality. When they do that, they may fall down into the sea, because they probably not properly process them. So, the bacteria probably not going to properly treated, so you can potentially have outbreak. But if you are a very conservative, want to over process it, you go this side, you are going to have more nutritional loss. You are much more safe, but you may be nutritionally losing things, because today's thermoprocess, many of the processing methods are like this. So, when you look at the non-thermal technology, how do you find that zone where you can have safe product without compromising the nutrition? So, I think that is probably the right window you have to identify. So, this slide just to show how the juice color parameters changes with the PEF intensity treatment. So, in general, PEF probably has less impact on flavor, and in fact, when you look at cranberry juice, PEF and a raw product, they have very similar flavor. Apple cider treated with PEF, there is no detectable difference between untreated and fresh. So, you can see that the PEF is kind of trying to give you almost like a fresh like product attribute from a quality, flavor, color point of view, but it also do that in microbiology, but spores not inactivated. So, it works well with some of the juice products. Same thing with color, you can able to preserve colors, and vitamin C probably can be preserved as well. Now, what is the application of PEF now? So, there is a company called Genesis Juice. They started PEF application with cold pasteurization for various juices, and they had a very promising results. And again, there was a management change, and then this has happened about 10-15 years ago. That company decided PEF is not a choice for them. They switched over to high pressure processing, and then they were doing mostly high pressure processing. So, that kind of resulted in that PEF application, the US kind of passed away. Whereas, in the Europe today, there are a number of companies kind of tend to use juices, treat with them PEF treatment. Part of the reason is it is the more perception from consumers and also the food processors. So, they worried about the energy use, they also worried about consumer perceptions. Long time ago, there was a focus group done at UC Davis, where consumer asked about different technologies, and US consumers particularly do not like to use for example, radiation, because they think radiation make product radioactive, even though scientifically that is not true, but that is the perception. When talked about electrical based technologies, they said, why do you electrocute my food? I do not like that. So, they kind of did not understand the purpose of adding electricity or electric field during processing. When they talk about high pressure processing, oh, my grandmother uses pressure cooker, why do you say high pressure is a new technology? Because they did not understand the extent of pressure used in high pressure processing, which is 87,000 psi, whereas in the pressure cooker it may be 50 or 100 psi, it is much lower, but they thought both pressures are same. Then when you further probe, the pressure treated product stay in your refrigerator 45 days or longer. The question was, what did you do to my product? It's normal for my product to spoil in about a week or 10 days. Why it's keeping that much? So they kind of start worrying about safety of that product, because the consumers probably do not understand the science, particularly food science. So consumer education is very critical in some of these new processing technologies. So PEF application now it's there for in wine processing, so that you can able to use sulfide so that you can stabilize the wine. A company in Chicago used the PEF treatment for wastewater treatment. So you do the PEF, so you reduce the bioburden so that the wastewater can be go well. More and more US companies now adopting PEF for French fry processing, because when you are French fry process, sorry, maybe I have a slide here. So when you are processing French fries, you're going to have the either you have to, you probably have a lot of breakages, and you have to either blanch with the heat treatment or other means. So now what they found is with electroporation, they able to adjust the turgor pressure so that you can able to easily cut the fruits and vegetable, and then you can able to use the PEF treated for French fry. So that also control the mass transfer of oil and water and so on and so forth. Other application of PEF is olive oil. So you can probably use, when you have olives, you can wash, crush, and then you can probably apply PEF, and then you also have the what they call malaxation. So it's kind of, you take the mass of all the olive in a crushed form, kind of knead, massage. During that time you can do PEF treatment, so it can help to extract oil better, and there are now big factories or PEF treatment chambers are available in Europe for these type of applications. So Europe have a little more PEF applications at the moment than the US. So you also have number of fruit juices being treated, and this slide just to show how the shelf life of an untreated product compared to the low intensity, high intensity PEF treatment, and you can see that the shelf life can be about 60 days, much more stable compared to the untreated samples. You can extract pigments, grapes pigments with the PEF treatment, and you can also like I think various juices can be extracted with the PEF treatment. Now this is a message I think I was kind of telling earlier. We have number of non-thermal novel technologies available in the market. So each has its own unique benefit and limitation, but at the moment one of the challenge is the consumers, in the sense if consumer not going to buy the product, these technologies never going to get into the marketplace, because consumers not going to buy the product for the sake of technology, they are buying the product for the sake of processing or for the sake of what benefits processing can bring in. So in the early days of pasteurization, so the Chicago Department of Health kind of tried to help explain why pasteurization of milk is important, good for children, because it is kind of removing all the disease and everything. And even today in the US, there are segments of population do not want to consume milk with either thermal or any other processing methods, but I think if you look at the benefits versus the risk, you probably have much safer product after pasteurization, and when you include the non-thermal pasteurization, even greater benefits. So I think one of the take home messages, the food scientists and engineers need to learn to communicate and better explain what we do to the lay public, so that they understand. because oftentimes people understand what farmers doing, people understand the processed product and nutrition side, they may not. So, food industry is kind of a legacy industry. So, you have to kind of probably need to convey the benefits of the technology. We need to overcome the limitations of the equipment, and so that you can able to make the non-thermal processing more effective for commodity processing in the future. So, in terms of PEF, the sterilization is not demonstrated, and you cannot process particulate foods, you cannot have air bubbles, and commercial equipment is relatively limited, even though in the last 5-10 years this is changing, and PEF cannot work well with the low moisture content food, and then like high pressure PEF may not work well with heavy metals and pesticide residue. Not much data is available, so we need to do that. So, in summary, PEF produces safe, very quality in foods, extraction, tissue structural modification, pasteurization are some of the applications, but in addition PEF can be used in cosmetic, pharmaceutical and other biofuel type industry as well. We can stop here and we can have some discussion.
Okay. Sir, I have a few questions. So, recently we wrote a paper, and it's also we wrote a paper on ANF. So, and we found that PF is mostly suitable for juice kind of things. But if you want to treat the sample with like solid or powder sample, it is not effective. So, for reducing the ANF and as well as to
Reducing what?
anti-nutritional factor.
Oh, anti-nutritional current. Okay, sure.
So, we found that in case of liquid it is more suitable. So, we also follow the Professor Indravati from New Zealand. I think she is working PF from decade ago.
Dr. Indravati?
From University of New Zealand, I think.
Right, I think that I probably know the some researchers there.
So, she also just recently explored how the PF will be advantage for protein application and modification. And so, what kind of progress or limitation the PF having for the large scale purpose if you want to treat the like powder sample?
So, like powder is a low moisture content type product.
Yes, sir. Yes.
So, it may not have much more effective, and again it also depends, are you looking at this as a microbial decontamination? It's not going to work. So I think PF may not be a good application there.
Okay. Sir, what is the basic difference between ohmic heating and pulse selective field? Both will be similar, na? Similar way. So
that's a good question. So if you look at ohmic heating, you are applying, you have two electrodes, and the voltage between the electrodes is probably 50 volt per centimeter, 60 volt per centimeter. Now they are going moderate electric field, which may be going to 100, 150 volt per centimeter and so on. The same thing if you look at PEF, that's going to be in kilovolt, not volt per centimeter. So it's like 35 volt per centimeter and so on.
okay.
So during ohmic heating, you are passing electricity between the voltage gradient, whereas in the case of PEF, you are delivering pulses in a very short time.
So mostly it is similar to the cold plasma. In case of cold plasma, reactive species will be passing through this. Here, like mostly electron or pulses will be passing through this.
Right.
Okay, that's why maybe it may be more suitable for juice product.
Right.
So, sir, what will be the future research scope for PEF? What's your opinion, sir?
So, I think it kind of depends on the applications, right. So, I think when the potato researchers, I think they were initially looking at this, they had a structural breakdown of tomato products with like before making French fries. They were experimenting, this is done in Germany. So, they were experimenting with PEF, and they eventually found they can able to modify the structure and then get the better product category after PEF treatment. So, previously that knowledge did not exist. So, I think like this probably some of the newer applications going to evolve with use. Other thing probably from a purely scientific point of view, you probably do not have a good scientific information what type of nutrition preservation in PEF. People always assume non-thermal, so you are going to preserve the nutrients, but there is no data
that
available.
That is not true for every case in
right.
certain
So, we need that data. Next one is how those nutrients going to interact with your gut microflora. That information probably is not so available. So, that is something probably need to evolve.
Okay, sir. Thank you.
I wanted to know why PEF is a non-thermal process. Why are we calling it a non-thermal process?
Again, that is a good question. So, there are two things. Scientifically speaking, high pressure PEF, even UV, many of these technologies are thermal processes. But you have a new set of industries who want to differentiate themselves from traditional thermal processing. So, the extent of thermal is lower compared to traditional thermal process. So, they kind of market themselves as a non-thermal. But strictly speaking, there is a temperature increase during high pressure, there is a temperature increase during PEF, and then you probably see similar things in other non-thermal technologies. One of the true non-thermal technology is probably radiation, but that probably because of the consumer concerns, it is never kind of fully utilized. We will talk about that in the next lecture.
Sure. Thank you so much. I also had another question about the previous process. Was there a specific reason why pressure was applied before heat in the flow chart for high pressure processing? Is there a specific reason why we are applying pressure and then we are applying heat?
Okay, so you are probably talking about the chart which shows the pressure temperature.
The pilot scale, yeah.
Pressure temperature history. So, there are two things, right. One, during high pressure processing, there is going to be a temperature increase due to isostatic compression. So, you apply certain megapascal pressure and correspondingly there is going to be a temperature increase. So, you may be referring pressure applied, then the heat is applied. So, that is because the temperature increase happening because of the pressurization. When you remove that pressure, that temperature goes away. So, that is probably one case. The second, in the case of pressure assisted thermal sterilization, normally we preheat the product, say 70 Celsius, and then load inside the pressure vessel. Then you apply the pressure, you are going to increase the temperature to conventional sterilization temperature like 120, 130 Celsius and so on. So, you have two type of scenarios.
Sure. Thank you.
Thank you. Mentioned in one of the earlier discussion, food radiation probably one of the classical technology that has been proven safe by so many different scientists and so many different government agencies around the globe. Yet, this is one of the technologies which is not commercially viable, or like it's not commercially practiced because of the lot of misunderstanding from consumers. So, the food radiation is relatively very simple. You take the product, you package it, and then you subject to certain ionization radiation, and the radiation source can be X-rays, gamma rays, electron beams, and it kind of has a certain energy dose called kilograys, and then you are going to treat that for a certain time, then you are done and your product is safe. It can be quite effective, inactivate virus, bacteria, parasites. It can do insects. It can do delay in maturation of fruits and vegetables. But one of the common concern is radiation kind of came in the 1900s and then subsequently evaluated in the 1950s and 60s. At about the same time, we had World War I and World War II, where the atomic bombs were developed and destroyed and so on. So, people were skeptical about radioactivity, and when you say I am using radiation, they also worried that radiation will make the food product radioactive. So, they worried they don't want to consume the product because they think, okay, that's going to make me sick, all those things. And they also worried that radiation make people with more cancer, birth defect, and so on. The other thing, people worried that companies can take a spoiled product, radiate it, and then make it better. Again, that's not true. You cannot take a spoiled product, use any technology to make it a good product. That's never going to happen. But that's a rumor people probably trying to spread because they worried about radiation. In 1905, the patent was issued for radiation. 1940s, MIT has done research with ground beef, and then one of the major milestones that changed the radiation life is 1958 Food Additive Amendment. The US Congress at the time decided that when you process food with radiation, you have to label that, and they consider this as an additive. So, what that means is when you are high pressure processing, you don't need to say in the labeling statement it's high pressure processed. When you are UV treating or you are using pasteurization, you don't need to say it's a UV pasteurized or thermally pasteurized. You have that product. Whereas, when you pasteurize or sterilize with radiation, you have to use a symbol called EDORA symbol, which we will show later, and that's called Food Additive Amendments. And as a result, whenever people see that radioactive, the EDORA symbol, their mind automatically goes to radioactivity, and then they say, okay, I don't want this product. So, it kind of became a major challenge. But otherwise, if you look at in 1970, astronauts goes into moon, they took radiated products with them, and then 1980s, WHO said, radioactive, radiation is safe. So, it's kind of repeated after repeated. Many different governments said it's safe, but the persistency of consumers, particularly in the US, has kind of become strong. In India, I think it's relatively acceptable, but many other countries it's not. Another interesting thing, at least from the US perspective, is whenever there's a major outbreak, consumer probably more receptive to accepting radiation, and with passage of time they forget that, and then they are against radiation. So, some of you probably too young to remember this, but probably in the 90s, there's a probably thing called Jack in the Box. There's a major meat outbreak in the one coastal area of US, and a lot of children died, a lot of people eating meat died. Then there's a major outcry why we don't invest in radiation so that we radiate beef so that it's safe. Then when the time passed, people become resistant. Then there are recently, for example, there are outbreaks with consumption of produce. Then people said, why we are not radiating produce with radiation with some of the leafy greens and so on. So that kind of ups and downs goes with the time, and but nevertheless, consumers always go back, it's negative. So that's a kind of an issue basing radiation. The other thing probably related to the radiation, people think the treatment facilities like where they have gamma rays and so on, they think it's like a nuclear reactor, and they think that if there's a meltdown of that gamma columns, it becomes, the neighborhood becomes radioactive, all those things, even though those type of fission type of things never happens with the radiation type applications. So there's a lot of misinformation, but over the years, whenever there's a major outbreak, the researchers always come back and show the benefits of radiation, whether it's a meat or fresh produce and various other applications. So this is one of the true non-thermal technology. You can package it, and you can even do this with the frozen conditions. There's no chemical preservative, so that means today we call this as a clean label, but this is demonstrated in the 50s and 60s without even knowing it's kind of the term. And it has a low energy. Today there's a lot of talk about sustainability, reducing energy use, and this is one of those things. And then you also have relatively lower operating cost. You probably have high operating costs. So this is a major issue, consumer acceptance. And then people worry about the resistance in microorganism, maybe radioactive more resistance. So there's a discussion about toxins. Many of the non-thermal technologies may not be good in inactivating toxins, and so that's potential. So the radiation is called so much energy. It's 1 kilogray means 1 kilojoules of energy per kilogram of treated product. So we kind of saw the term pasteurization and sterilization. Same thing can be adapted for here. What they mean reduration, they apply 1 to 5 kilogray. This reduce spoilage microorganisms, so increase the shelf life. Radiation means a little bit higher dose. It may be more like pasteurization. Radioapatization means greater than 10 kilogray for commercial sterilization. So a lot of times they limit this high dose maybe around 30, 40 kilogray, so that you kind of have more controlled radiation treatment for sterilization applications. Low dose means you can able to control the insect grains, sprouting, you can ripening, prevent delay the ripening, reduce the problem with parasites and so on. So it's kind of very mild, but effective in number of different ways. Medium dose, it's more pasteurization, like you can do inactivate various vegetative bacteria, and then the more growth fruits. High dose is more commercial sterilization, and you can able to sterilize the food, and then you can able to make that safe. So radiation can be delivered by 3 different means: gamma ray, X-ray, and E-beam. These are all same dose of radiation, but gamma rays comes from more natural source. E-beam and X-ray, these are human made, so that means it's made. So when it's a natural, that means you going to constantly deliver that radiation dose. Whereas E-beam and X-ray, like the Tyndall X-ray, you go to the doctor, you can turn it on when you want it and you can turn it off when you don't need it. So, gamma rays is more commonly used, and it's basically coming from cobalt 60 cesium 137, and usually this is kind of come in the shape of a rod, and then you tip the rod inside a big water pool, and when you want to use it, you raise the rod up and then you kind of bring the product, just pass around the rod so that it receives the radiation treatment. I have a better picture in the next slide or two. And the one of the things is, since it's always on, you have to shield it. So, that means you have to place inside a 7-meter depth of water, or you can put inside a concrete column. So, in other words, this radiation is only for the food, but if you operator for some reason get into that, you will see later on some slide, we are very susceptible to radiation. We will get sick or die eventually if you expose the radiation. So, that is where you have to kind of do it, but we are not going to die by consuming radiated product, because radiated products never become radioactive. So, gamma rays here, like I think you have some source of gamma rays, and then you are going to expose the product, and then it kind of gets this treated. Now, if you look at there, I mentioned concrete or aluminum lead for preventing radiation coming there, because lead or concrete is quite effective in stopping the radiation. So, when it comes to a lead door, it is not going to pass through. If it is a concrete door, it is not going to pass through. Otherwise, paper, metals like aluminum, it can penetrate. So, it is kind of quite effective in that sense. Now, ionization radiation, remember, this is a form of energy. So, that means it is similar to microwave, infrared radiation. Like yesterday we saw some of the ionization, like I think electromagnetic spectrum. This is the gamma rays in the one end of the spectrum, and so that means it's end of the spectrum. This has a high, so that's very effective in area, but without destroying the nutrients. So, if you have a radiation plant, gamma radiation plant, you technically it's in one location, and you may have prepared your product, ship them to your facility, and they may be loading them, and then let us say that they are going to send this into a conveyor belt, and then it is going to go through this treatment chamber. In the treatment chamber, you are going to have several of these radiation room with this radiation gamma tools. So, the conveyor belt is going to go around that, so that the conveyor is moving a particular speed. So, you can control how much time the product is sending near that treatment zone, and you also turn them both left and right, so that you can see that the product is exposed all around, so that you receive the proper treatment. After treatment, the products come here, and then you can do unload, and then you can distribute, and so on. So, when the treatment chamber is not in use, these bars, they are going to be lowered inside this storage pool. Like remember I said a big water pool, you can put it inside, so that they do not operation. E-beam, it is a human made, it is a lower energy compared to the gamma rays. It has a longer wavelength, it has a lower penetration, it also has on-off capability. You can use a linear accelerator to produce, and you have a maximum energy about 10 milli electrovolt, It's not radioactive, but it doesn't have as much penetration as gamma rays, but you can able to shorter exposure time. So, again you have a linear accelerator, you treat the product, or you have a beef and then you can pass it through a conveyor belt and then you kind of expose. So, you adjust the speed of the conveyor belt so that you can able to adjust the treatment time. So, like I think these type of things are good for ground patties. Again you can process quite a bit, and then the cost is about 2 cents per pound in the implant system. X-rays, these are similar to the tendal X-rays. You may go visit the doctor, and here your electron beam is accelerated and collide with a metal target like tendula, and on you are going to have the generated, and again you expose the product for certain time and you can able to get the treatment done. One of the things, remember, in all these technologies we always emphasize on the uniformity of the treatment. So, in this case the ionization radiation is a uniformity. Let us suppose you have a big beef patties here. So, when you do the treatment, you are going to apply only in the top, it may only go so much depth, the bottom portion may not treat it well. So, you may have to make sure that you treat both up as well as down, so that it is kind of treat much more uniformly. So, that some dose the is received, but maybe kind of look at make sure that that's sufficient to kill your dark bacteria. The same way, packaging has to be properly selected, so that the do not create and radiation packages. Some packages chemicals react with radiation and produce what they call radiolytic compounds that may be harmful to human health. So, you have to what they call pre-qualification of packaging material. So, in other words, you are a person interested in radiation of some beef patty or vegetable, you have to select a approval list of packages, so that they are free from some of those effects. So, if you have don't properly select that, then you are going to have incomplete penetration, but because the package does not allow that, and then this is to uneven dosage, then you are going to have potential problem. Now, there are something called dosimeters are used to measure radiation. So, remember we talked about conveyor belt, where the product is going through the radiation room and then comes out. So, oftentimes they along that product they put a small miniature disc, like for today's, if you want to compare, these are like you have this small Apple tracking devices, where you can kind of know where the location of your package and so on. It is kind of similar to small chip like thing, you can put inside the product, but they have certain chemical compounds like alanine, amino acids or dyes and so on and so forth, that change their property with the exposed radiation. So, with that they can able to measure whether or not that batch of samples receive proper dose of radiation, because we do not have a thermocouple, we do not have a pressure transducer to measure the ionization radiation, whereas the dosimeter can help to measure that. The other thing is, oftentimes people do not or when the radiation room is active, operators do not go inside that radiation room, but nevertheless after finishing that they may have to go back and inspect all those things. then they have to carry the dosimeter just in case there is a radioactive leak, is any accidentally they exposed, that the dosimeter can help to identify some of those potential risks. Now, the microbial kinetic parameters, we talked about d value, the same d value concept can be applied here. So, usually it kind of lists as a D10, and then you have d values measured in the room temperature or freezing conditions, and then atmospheric conditions and so on. So, if you look at here, the d values for viruses 10 to 200, bacteria 10 to 50, insect 0 to 0.01 to 1, and higher animals you can see 0.005 to 0.1. The higher animals include humans. So, that means we are highly susceptible to radiation. So, that is where you have to make sure that you properly protect yourself as an operator before getting to the radiation room. Whereas, if you look at here, bacteria has a 0.1, 0.5 to 10, whereas viruses you probably 10 to 200. So, they are more resistant than the bacteria. Why? We will kind of explain that in a minute. And then the other thing is, if you look at the fresh versus frozen product, you can see that E. coli has 0.24 to 27, 0.31 to 0.4, Listeria 0.27 to 1, 0.5 to 1.3. So, the idea here is the fresh has relatively less resistant, the frozen is a little bit more resistant. The reason is when you freeze, the available water is kind of frozen. So, that means they are not readily available for the microbes. So, that means when you send the radiation, that radiation signal or dose is not transmitted to the microbes. So, they tend to have higher resistance, but nevertheless you can able to inactivate them with a little bit larger dose. The type of food, that means the complex food have a more resistance than the simpler food. Moisture content, again with the lower water activity, you are going to have less effective, like many of the treatments, probably like whether it is a thermal process, high pressure process, PEF, many of the technologies, they are not effective with the low moisture content food. And here the dosage levels for different leafy greens and microorganisms are given, and then again you can see that you are going to have different different products, different microorganisms have different sensitivity. Again, this is the data for different meat products with the different microorganisms. So, generally like many other processes, when you treat at room temperature it is effective, but when you add some more heat it is even more effective, and because the microorganism repair mechanisms are impaired by high temperatures. Same way when you freeze it, it immobilizes the water and prevents the diffusion of free radicals to the microorganism. So, they tend to have a little bit more resistant compared to room temperature. Other thing, if you do not have air, anaerobic conditions, it is also less lethal effect in the with the radiation, and when you have more oxygen content, you can have more lethal effect. And you also similar to high pressure PEF, some of these microorganisms can be sublethally injured. So, that means when you allow the right conditions and nutritious medium, it allows the growth and recovery of the microorganism. So, you have to pay accordingly. Generally, the gram negative organisms, gram positive organisms are kind of easily inactivated, whereas spores and viruses have most resistant because of that chemical and structural property, and then how they recover from the injury. One of the things is lot of the vegetative bacteria, they are going to have DNA, and radiation can affect the cellular function. They break the cellular strand or double strands, so that they do not function. When you look at viruses, they probably do not have that, they are very tiny particle. So, that is why they tend to be more resistant compared to vegetative bacteria. This slide, just to illustrate the same point we talked in the earlier slide, you have to compare the dose requirement for keeping the product safe against the dose needed for keeping the product proper quality, and then there is a balance between these two. And if you make error in one side, you are going to have a food safety problem. If you make error in the other side, you have over processing. So, for example, you have observed dose and certain effect on the quality. So, this is the minimum dose where you may be killing all the vegetative bacteria, E. coli and things like that. And then this is a dose where you are going to have all these quality issues, lipid oxidation, color change, off flavor and so on. And you can see that there is a small window here where you can kill the bacteria effectively, but you do not have quality issues. Whereas, if you go this side, lot of high dose, you are going to have quality problem, whereas if you come in the other side here, you are going to have a food safety problem. So, you kind of want to avoid this and try to have a proper window where you can have both food safety and quality. Because I think today, in the interest of maintaining food quality, sometimes people just overlook the food safety, but you have to kind of try to make sure that food safe, because people do not mind if the quality is a little bad, sometimes they are okay, but nobody want to eat a product and die, even if it is a premium quality. So, you kind of want to pay attention to that. Packaging, pre-qualification is needed, because sometime if you do not have certain packaging compounds, you are going to have a related compounds formed, and that may result in migration of compounds, which is not good. So, you kind of want to avoid some of those there, so that you have package with the proper shelf life. So, in 1966, FDA required labeling of radiated products, and so since 86 they started using the RIDA symbol, and so that means you have to show this symbol here, which shows treated with the radiation. So, now if you the only exempt is ingredients. So, that means if you are processing a big batch of vegetables, fruits, or you have a meat product which is consumed normally part of the meal, you have to use the radiation symbol, and then when people see that, they may kind of get a little bit negative perception. On the other hand, the ingredients are exempt. One of the commercially available ingredient today, most of the places, which is radiation treated. Anybody know what it is? A product which is treated radiation wise, but it is commercially available, spices, because normally spices could be treated with ethylene oxide or some other chemicals, but people do not want the chemicals. So, that is where it is radiated, but since nobody is using say half a pound of spice part of their meal, it is only add a small quantity, you do not need to declare that part of the labeling statement. So, that is where consumers consuming spices, but not necessarily worried about radiation effects. So, because of that Congress thing, radiation is classified as a additive, and that is why it is part of the statement. And with the packaging, FDA required pre-market approval, and that can be very lengthy process. Now, different countries probably reviewed radiation and kind of mentioned it's safe, including FAO, Food and Health, FAO, Food and Agriculture Organization, Codex, things like that, but usually they are all very positive. On the other hand, the consumer acceptance kind of vary. So, for example, Brazilian consumers are more positive, whereas European consumers tend to be a little more negative. US consumers are negative towards radiation. So, I think the consumer education is a key trying to improve the consumer acceptance of radiation product. And part of the reason today is lot of the, with urbanization and globalization, lot of the consumers removed from the farm, they do not know how the products are grown in the farm and things of that nature. So, for example, an average urban kid may not know where the milk is coming from. To them it may be coming from the grocery store rather than from the farm cow and so on and so forth. So, this is where the consumer education, how different process technologies help to preserve the product, help to preserve the quality and nutrition probably is important. And in that sense, radiation is a very wonderful technology, scientifically very sound one, but it is underutilized because of the lack of consumer acceptance under the current circumstances. I kind of mentioned earlier, people kind of spread a lot of misinformation. Radiation use may lead to the meltdown in a gamma radiation facility. The facility can explode because it has a lot of fissionable material, or they worry that it maybe has food become radioactive, or it creates a lot of radiolytic chemical compounds, and they allow the treated spoiled food with radiation and make it fresh. But if you look at some of these things, even thermoprocessing, the same thing can be said. You can take a spoiled food and treat it and then make it safe, but nobody worry about thermoprocessing because people feel comfortable, whereas radiation, something the unknown technology, they fear about it, and that is where a lot of the misinformation may be coming from. So, in summary, radiation show a lot of promises in maintaining safety, sensitive properties and shelf life, but it is very poorly understood. It kind of create a lot of confusion and misunderstanding. As a result, it is a underutilized technology. So, one of the key challenges, try to overcome that and then try to do better education with the consumer education. And how do you do that, and how do you educate the consumer and then maximize the benefit of radiation is probably a challenge for both food scientists as well as the food processors. And here are some selected readings, and I will be happy to have some discussion.
Hello, sir. Sir, my questions are too basic and can be the consumer oriented. So, isn't it authorities making a consciousness or bringing a consciousness in the mind of consumer by putting the Rudda symbol? If it is acceptable or in the acceptable limit, it is safe. So, why to put the Rudda symbol on those products? Because we are not labeling. We are trying to hide the labeling as over processing or processing parameter. So, isn't it there the it is the intervention of authorities which is making the people to have a consciousness that it is unsafe?
Right. The concept of Idora simple specifically applicable the products made and sold in the United States, where the US regulations require any irradiated product to have that symbol there, because its irradiation is considered as a food additive. So, it is an act of Congress. Only the Congress needs to redo that legislation so that they remove that requirement. But with the legislation process, there are so many priorities. This is one of the lesser priority. It did not get the traction, so that they did not have that done.
So second question is sir, we are listening about the term radiation processing. Sir, just as we pronounce or we put these words into the picture, then it creates a bad impression on consumer. I have seen just like on the first day also, we have taken the example that even the director of such a premier institute in India is also taking that word, has a bad impression in the back of the mind, in the subconscious mind. So being the food engineering background people, where we are losing control, that we are not able to justify us.
Right. Like again, there are people talked about using different terms for radiation. Instead of using radiation, cold, cool radiation or something, I probably don't remember at the moment. But I think still in the broader literature, the term radiation is there, so it's kind of what used. But maybe perhaps a different branding of the technology name may help, but that probably takes time and effort and communicate that benefits to the consumers.
Yes, sir. Sir, since we are talking the technologies such as pasteurization, sir, you told the example, it is sir 70s, 80s times of times technology. But sir, where we are lacking, my main concern is where we are lacking, or the industries are lacking, or the authorities are lacking, that we are not able to synchronize us to deliver the benefits to the consumer. Where we are lacking, it is the academic problem or industries or whole as an integrated problem of a society, or it is a consumer unacceptability of the processed food.
Right. As far as radiation is concerned, the discussion I had is primarily limited to US, but I think it may be similar here or different in India. And again, it's probably country to country, different countries have different regulations. But in overall, this particular problem came from the more what I call rule making process rather than scientific one. And then that presence of that symbol constantly reinforce the consumers something about this, because they don't see that symbol for thermally pasteurized products or even high pressure pasteurized products, because these are all considered physical processes, whereas in radiation it's there, so that's why it reinforces. So I think it understand that, but I think it's probably something. There are organizations trying to address this, but so far this has been a limitation.
Sir, just I have one question about the HPP one. HPP,
Sure,
high
yeah.
pressure processing. Sir, we are talking about the high pressure processing. Sir, in process we are dealing with the immense pressure. Sir, so are we in the status, social status, that we can employ that unit in the industries, because industries are located nearby the cities only. So if it collapse or a pressure leak is there, sir, it could be more than hazardous what we can think, because it can collapse around I think I was hearing about analogy that it can collapse the building of entire agriculture department of IIT Kharagpur if it pressure leak is there. So sir, we are in social status in USA or in India that we can employ that.
Sure. So that's again part of the misinformation. So high pressure processing, the technology equipment kind of originally developed and devised from material science or those type of engineering disciplines, and the pressure vessels are designed and fabricated as per what they call American Society of Mechanical Engineers ASME code. Okay. So with that, what they also have, they probably have some built-in safety mechanism so that the pressure vessels doesn't explode and disintegrate. Number one, they have this wire wound concept, so it can expand, contract, rather than just bust into small pieces. So, I think that is number one. Second, many of them probably have a built-in what they call safety disk. So, what that means is, let us say for some reason the pump decide to keep pumping more and more fluid. Let us say you set 600 megapascal, pump want to built in say 1000 megapascal. The safety disk is probably have a safety mechanism, it busts to open say 600 megapascal, 650 megapascal, so that the pressure buildup going to stop and it is not going to happen. So, most of the high pressure vessels using the commercial equipment today, they are built with wire wound technology, and all of them have this safety mechanisms part of the built-in process. So, you never going to happen some of those issues.
Sir, could you please repeat the first one? First reason, first what you have told. Sir, you have told the two aspects. Sir, first what you have told, I am not able to
Okay, so
get it.
can you so what is the second reason I said, like the okay, so first one is probably the wire wound technology. So, you can have a pressure vessel monoblock. So, that means you can just take a piece of steel and have a pressure chamber, and then with the repeater use, that pressure chamber can create a crack, and that is where you can say crack open that can burst into pieces. But that type of vessels not used in the industrial scale. They are using wire wound technology. So, that means they take pre-stressed steel and then they kind of form a wire like chamber that can expand, contract within the pressure levels, so that they can be much more flexible and nimble.
Thank you, sir.
Thank you.